variant Rom-Kedar, who will tell us about some Hamiltonian impact-like systems.
Okay, thank you for coming, and thank you, Shira, for inviting me. Speak in this place. I'm honored. So I will talk about an approach we developed in the last 20 or so years for looking at Hamiltonian on the dynamics of Hamiltonian-like systems, and work with quite a lot of people that I will point out as it goes. And please feel free to ask questions. So what I will talk about are billiard-like and impact-like systems, which are mechanical Hamiltonian systems in which the potential has some very sharp fronts that can be, in the limit, thought of as hard walls. And the idea in these works is to try to use this very singular limit to understand what kind of dynamics we're going to get. And I will start with a more precise statement of what are the kinds of systems we look like at and what is the motivation. And then I will tell you about two families of such systems for which we can say quite a lot about the dynamics. So just to remind ourselves that the field of smooth mechanical Hamiltonians is a very old field, of course. So that's when I talk about mechanical Hamiltonian, I will really think about the simplest possible case in coordinates. We have kinetic energy plus a potential energy, and if the potential energy is smooth, the question what happens is a difficult one. This is from the days of Poincaré that said that if we want to understand a dynamical system, we should the ultimate goal in understanding a dynamical system is to understand, to classify all kinds of solutions that are going to appear in such a system, to classify or to divide phase space to regions that behave in a similar way, etc. And can you do it for such systems when they're nonlinear? In general, we don't know how to do it. And there are only very specific limits in which we can. And one of them are the integrable systems when there are n constants of motion. And then you know that for almost all initial conditions, for almost all level sets, we're going to have quasi-periodic motion on tori. How these families of tori connect to each other is, in fact, can be quite complicated. So there is a large community that works on integrable systems just for that. But then the things that I will more concentrate on is to say, well, if you know something about the integrable system, what do you know when you perturb it a little bit? What can you say about the dynamics close to it? In the smooth case, we have the KM theory. And when we go farther away from this to the mixed phase space region, we even know less, but there are some there is a huge body of work that works these things. And in particular, so these are the kind of tools that are being developed, I would say, for more than 100 years. One of the questions that is still open till today is, can you have smooth dynamics of this kind, which is hyperbolic? And one of the, because once you have the hyperbolicity, you can start to talk about statistical properties of the solutions and the nice things like that. And people have realized that while in the smooth categories, these are hard questions. If you look at billiards, you can get quite more understanding of systems which are far from integrable. In particular, for the billiards, in addition to the two examples of integrable tables and billiards, should I remind what it means? Okay. So there are the integrable tables, and there is this class of hyperbolic or Sinai tables, Movich tables, which have hyperbolic dynamics and ergodic and mixing and all the good things that one can hope for. There are also other classes which do not exist in the smooth case, which are systems with sharp components. So you can have here these Mimovich mushrooms in which you have both hyperbolic part and an elliptic part. And you have also these quasi-integrable billiards, which are very interesting. For example, polygonal billiards, or billiards in which you use confocal sizes of the ellipse to define the billiard table. And they have these funny property that on one hand, they have some constants of motion, and on the other hand, the motion is more interesting. I will get a bit more to it later on. So the question is, can we use some of the knowledge or some of the techniques that are known for the billiard world to understand what happens to the smooth Hamiltonians when they are close to being billiard-like? And these are these works that, on billiard-like potentials, in which we look at a potential function which is smooth for any positive epsilon, but has a singular limit. When epsilon goes to zero, it goes to zero inside the domain and to infinity on its boundary. And what can we say about the dynamics of such smooth system? If we know, for example, that the billiard is a dispersive billiard, which is chaotic. And we developed with, this is with Dima Turaev, and later on also with the student Anna Rappaport and Dima, we derived the methodology to understand such systems. And the way and there were two important steps in this methodology. The first one is to rewrite the potential as a composed function of the barrier and pattern function. The pattern function is a regular function in epsilon, which just gives us the level sets of the potential. So it depends smoothly on epsilon and has nice limits in CR. The barrier potential, okay, is the one that includes all the singularity in epsilon. So this is the function which goes to infinity on the boundary and to zero in the interior, as its one variable q goes, say, to zero. Okay, and in this way, so this is like the barrier function and the pattern function, say, in 3D billiards, and for 2D billiards is of course even easier to think about it. And the idea is, with writing it in this way, is that we get one-dimensional dynamics near the boundary. The second idea is that, as opposed to, and so when people analyze the billiard dynamics, many times they analyze what's called the billiard map, right? So the billiard map takes you from one point on the boundary to the other point on the boundary, the angles, etc. But this is not a good idea if you are starting to smooth your potential, because then you don't reach the boundary really. And you have a problem with defining a good section. And so the idea we used all the time is that instead of looking at the boundary, we look at some interior sections and look at return maps to interior sections. And in this way, you can, and in this way, you can prove quite easily the following kind of theorem. So you use, first of all, so you use these sections which are interior to your domain. You use, and this is theorems which we proved, that when you go from one section to another with not close to the singularity set. So when you have regular reflections, these maps are going to be close to each other in the smooth, in CR smooth category. as epsilon goes to 0. And therefore, when you compose several of such maps, you actually get that the return map is a CR perturbation, the return map of the smooth system, even though the limit is singular, it is CR close to the map of the billiard. And that allows to prove quickly that and immediately that hyperbolic periodic orbits and hyperbolic sets persist. Elliptic periodic orbits provided your non-resonance conditions. So you can think about it as running sufficiently fast along, it will also persist, etc. So that shows you that regular, the combination of these two allow you to get all kinds of persistent results on one hand, and on the other hand, they also let you understand what to do near singularities. Because near singularities, you can treat each singularity separately, and near the singularity, you have to analyze carefully the return map, or the map and its dependence on epsilon, but you have here essentially one-dimensional dynamics because of the way we wrote the potential. So you know how to do it. And once you write it, you can start to ask what will happen to singular structures under the smoothing. And for example, one of the important results we had in this direction is to show that when you smooth a Sinai billiard, you make it non-ergodic. You create stable periodic orbits. And we started with a theoretical derivation of that and a limiting return map. So this is like a numerical simulation of the limiting return map that you write near a tangent periodic orbit. So L is a tangent periodic orbit, has one tangency. We put it in a family of billiards with moving boundary. So, I mean, with a parameter that, not moving boundary, but a parameter that controls this boundary. So, so when gamma is positive, you have two hyperbolic periodic orbits, and when gamma is negative, you have none. And what we show is that right near such a periodic orbit, you will always get a stable periodic orbit for the smooth field. So you destroy ergodicity. And this was in 2 dimensions at the beginning. And then 10 years later, we came up with a Sinai billiard in n dimensions that also has this destroyed, that has a stable periodic orbit. But this Sinai billiard is in fact not does not correspond to n-particle billiards. It's a billiard with a very specific symmetry. And then very recently, Turaev and myself have shown that in fact, even the n-particle problem, so we have n-particle problems either in a convex billiard or in a box, and we put n particles here, and we put smooth potentials on the particles and on the box, and for arbitrary small epsilon, this is not ergodic. A positive volume of initial conditions which are k and stable. And all this is again using this technology. Okay, so this was all about billiard-like potentials, and the main achievements we got from it are this persistence of hyperbolic sets, elliptic periodic orbits for a large set of energies, and proof of non-ergodicity in Sinai-like settings, in 2D, in ND, and also for the n-particle problem. Okay, so what I'm trying to say, going back to our smooth mechanical Hamiltonian picture and billiard picture, is that we now sort of understand how these hyperbolic systems are going so far to be non-hyperbolic or near hyperbolic when you go to the smooth category, and whether or not hyperbolic systems exist is still an open question. So this was all about billiard-like, and now I would like to talk about impact-like. So billiard-like assumes that your potential is essentially zero at inside and infinity on the boundary, but there are many problems in physics in which you don't want to think about this limit. You want to think about the case in which in the interior you have some topography. For example, if you look at a triatomic collinear reaction, so you think about two atoms that are bounded to a molecule, and there is a third atom that's going to hit it, and you want to know whether it will combine with and you will have an AB molecule, or maybe it will reflect back. This is described by a 2-degree of freedom Hamiltonian, which basically looks at the distance between the RAB and RBC. And the type of potential you get here has very sharp boundary, thinking about the atomic repulsion forces, and then a nice smooth part here that corresponds to the van der Waals attraction forces. Okay? Because if it was just 3 billiard balls, they will never stay together. Right? So you need some, and you want to work, so you can think about it as billiard balls if you go to very, very high energy, but this is not interesting from a chemical point of view because you don't have molecules there. So you are interested exactly in the energy regimes in which you have both the attraction part and the very steep potential part. And you can now use the same kind of technology we developed for the billiard-like to look at such systems. So you can think about a Hamiltonian system with some smooth dynamics that occurs inside the domain, and a billiard-like potential that governs the reflections from the boundary. And in principle, you can think that the same kind of methodologies we did before should work here. In the case of this case was with Lev Lerman was and Marie Klotz were the motivating example for looking at impact-like systems. And there, for example, we could imitate this kind of potential that you see in chemistry books by a potential which has a billiard-like boundary in the shape of a corner, where the corner is actually the value of the angle here is determined by the masses of the 3 atoms, and then imitating the smooth part by just taking a potential which is quadratic with the saddle point in the saddle, and then we get at least pictorially something which looks very similar to these more involved models that are used in chemistry. So now the question is, what can you do analytically with such models in which you look at impact systems and their smooth counterpart? And the main problem here, you remember with the Hamiltonian, with the billiards, we had quite a lot of categories in which we could understand what is the motion for the billiards. What do we know about Hamiltonian impact system? It's much more, it's combining something you don't know about smooth systems and billiard-like systems, so it can be incredibly complicated. And the first observation, and this was with Michal Pnueli, was that we can talk now about integrable Hamiltonian impact systems. So in fact, when you come to think about it, for billiards, there are only 2 examples of integrable billiards. These are the ellipses and rectangles. Here we have a huge class of systems, and these are the systems in which you preserve the symmetries both by the smooth Hamiltonians and the impact surfaces. People, in fact, looked at ellipses with some polynomial potentials and found integrable cases, but what we are saying is, in some sense, that for systems of this sort, the number of potentials that will give us integrable dynamics is unlimited, right? Because all we say here is the following: take any product system of the sum of two 1 degree of freedom systems, or if you want in higher dimension, the sum of n 1 degree of freedom systems, and put the wall of the billiard to be aligned with one of the coordinates. Okay, then in this case, right, if you hit the boundary, P1 goes to minus P1, so your constants of motion are not changing. And in fact, in this case, you immediately get that the motion appears, right? So in the smooth case, the motion appears along, mostly along tori, and here it will also be along tori, but the tori will be cut, will not be smooth. And then you can start to play with the formations of these billiards. So now we got this whole new class of integrable systems, Hamiltonian systems, integrable Hamiltonian systems with impacts. And we can now play the same way that people play with smooth system, asking what happens when you perturb them. And here you can perturb them in different ways. You can perturb them by adding a smooth potential that couples the two systems. You can perturb them by changing a little bit the boundary, changing the wall, and you can perturb them by using impact-like potential and then making them near smooth. But this is, just to remind you, taking it in the smooth case with sharp boundary, this is a very strong perturbation of the unperturbed problem, right? It's not KM smooth, right? And still, the point is that with using the same methodology or similar ideas as we had before, we can analyze such systems. So, for example, one of the things that we can do here is look at the structure of the energy surfaces. Okay, so these are 2 degree of freedom systems, and have 3-dimensional energy surfaces. And the 3-dimensional energy surface for the integrable limit, of course, are just families of tori and some singular level sets in which tori combine together. But also when you add a perturbation, you don't have the division to level sets, but you have to stay on an energy surface. And therefore, once you understand the structure of energy surface, you understand that when you add a small perturbation, you have to remain near it, and the dynamics on it can be changed. But again, KM theory, etc., can tell you how. So for integrable smooth systems, Fomenko and his school developed this description of how the energy manifold, how the energy surface change using these Fomenko graphs. And these Fomenko graphs basically tell you, so here it's a simple example in which you have a damping oscillator, a figure 8 oscillator in 1 degree of freedom, and a regular oscillator in the other degree of freedom. And so when you have low energy, basically the energy surfaces have 2 components, one corresponding to sitting in one minima and the other in the other. And the Fomenko graph corresponds thus to these 2 lines, which tell you that you have these, if you want, this parabola multiplied by this one. So you have these spheres. And when you increase the energy, there is an energy value at which a change in the energy structure occurs when the two parts meet. And after that, you have one energy surface like that. And that's for the smooth case. And what we are saying is now you can do similar classification of the energy surfaces with the impacts. Okay, so you can take the impact surface to be horizontal or vertical. And then in addition to what we had before, we're going to have regions of impact and regions of no impact, which means that when you, so this is like an example of this classification when you have an impact, and you now can understand that some of these tori are going to be these cut tori, and in particular, there's going to be always a critical torus at which you will have tangency with the wall. Okay. Next, we can ask, okay, skip this. So this is global information to understand once we know that there are parts of the phase space which never hit the wall and parts of the phase space that are going to hit the wall, we can ask what happens under perturbation, as we mentioned before. And this is what I call local information. So basically, you can, I recall that when you want to know what happens near a smooth torus, a good way to do it is to look at a return map to a section to the torus, to a transverse section to the flow. And what you get for this return map is going to be, right, for the flow, right? So a return map, each level set is a torus. The transformation to action angle coordinates give you a directional flow on the torus. And the return map on the torus gives you a rotation. And when you combine many of such things, you get a twist map. And when you perturb it, the section, again, we take a section which is away from the wall, the section is still transverse, and we get a near integrable twist map, and therefore we can use KM theory, etc., to establish that, yeah, this is what I do here. So when we are away from tangency, okay, the map is CR twist map, and when we perturb it, we get a CR near integrable twist map, so we can prove KM theory for these far from smooth systems. Okay, this is as long as we are away from the tangent torus, and here are some numerical verification of these statements, and again we have a theory that essentially says that all these perturbations are okay because the return map that we get, which is away from the tangency, is essentially a perturbed CR smooth twist map. What happens when you are close to the tangency? So close to the tangency, the return map is not smooth. In fact, it is only C0 and not CR. And therefore, to get the dynamics near this torus, you need to work harder. And again, the upshot here is that by carefully analyzing what happens close to the singularity, you can write the return map as a map which is non-smooth. Okay. It has a square root singularity for negative k. K will be the distance from the tangent coordinate. And this map is quite interesting. So again, I'm not sure how familiar you are with these works on the standard map. Here. Okay, so yeah. So this is what is called in the literature, I would say, the generalized standard map. It's a twist map in theta, Okay, when epsilon equal to 0, you basically say that I is the same, the action is not changing, and theta is moving with a different velocity at each level of I. Okay. Twist means that theta prime of I is non-zero. So you move faster, say, when you go up in I. And then the perturbation to it changes the value of I. Okay. And a priori, you could think that once you, you take here F to have average 0. Okay. So a priori, you could think that maybe you start in some level and you could go very far up. But in fact, such systems with a twist, it's a theorem that if F is sufficiently smooth, you will get Km tori, so which will bend your motion. Okay? So when this Km theory works, I mean, these little islands are exactly places in which your frequency is rational. So when the frequency is rational, you can have resonances, and when it's irrational, you get Km theory. And as epsilon goes to 0, these resonances get smaller and smaller. Okay, so this is, and there are hundreds of papers on analyzing things that are related to such maps. What we show here is that when near tangency, you have a map which is similar without this red circle. It's the same as the standard map, just written in different coordinates, because here the coordinates are distance from the tangent torus. But now we add to it a part which is non-smooth. And then all the theorems actually do not work. And what can one prove about such a map? Well, first of all, we looked at it numerically. And we looked, so this map has a singularity at k equal to 0. Okay. And if you look away from k equal to 0, or at the invariant curves that do not hit k equal to 0, then you can use previous theory of Kn. There's no problem. So the only problem is to understand what happens in this tangency band, which is all the forward and backward iterates of this tangency. And we have some results about these things, for example, showing that when your frequency is non-zero, the size of this band is of order epsilon, and when it is has resonances, it has this funny asymmetric behavior. And yeah, and that's all I want to say about these near-integrable Hamiltonian systems. Summarizing what I said so far, I said too many things maybe, is that for the near-integrable Hamiltonian impact systems that we constructed, we know how to construct these impact Fomenko graphs and impact energy momentum bifurcation diagram. That standard map near regular impact tori give us Km theory, even when we take all the epsilons to 0, when we take the epsilons to 0. That near the tangency, we write up what this tangency standard map, but this is only for the case in which the coupling epsilon is non-zero. We don't know how to do it for the sharp potential case, and there are some open questions about this.
So in some of the two pictures before, there's some diagrams. So there was a number 1 plus square root 5 half Gonen ratio. What was that? I think.
This one, yeah. So this is the most right. This is in these standard maps. You have the frequency near which you work, the I value near which you work, and the most robust Diophantine number is this Golden ratio. So it's like quite standard to use that one.
Okay, so. But also appears when they do embeddings of ellipsoids with certain eccentricity into smooth balls.
Okay.
So that's embedded. So there's symplectic embeddings, and then you change, so you have an ellipsoid. So these are the so in dimension 4, where A is the cross ratio, 2 harmonic oscillators on the energy surface. So you write, say, E of 1 comma A. So keep 1, and then you have to scale that thing and embed it symplectically into a ball of radius 1, let's say. And then when you change this number A, then you get staircases how you can embed what's the maximum embedding, and the golden ratio appears. So and of course, so you know,
Okay.
So this is a map in dimension 2. And if you write down a flow, you get something on a 3. You could presumably take a mapping cylinder, so you get a 3-dimensional thing. So maybe.
But here, any J Fontaine number would work, or?
Yeah. This is just an example, a numerical example. So the map itself is right. The map itself is here, and what we get is the theorem tells us that when this omega is irrational, then you will have the band will be of order epsilon, the width of it will be of order epsilon, and the numerics for taking omega to be the golden mean was just to show that it works for this omega. But in fact, even when we take omega, this is something we don't quite understand. Even when we take omega, which is rational, it's not 0 or 2 pi, or not multiple of 2 pi, we also get something which is very similar. We don't understand why. I mean, the theory does not explain us.
But you took this here because of stability purposes. So
yeah, just to show. I think. I mean, we could have. I mean, we get very similar picture when we use other omegas. The only ones that give us very different behavior is when we take omega to be multiple of 2 pi, because then you have fixed points, and so the strongest resonances seem to behave very differently, whereas the weaker resonance appear to be not so different from the Fontaine case. But again, this is just numerics. It's not. We don't have good explanation of that. And one of the questions that we have also there is whether or not there exists a circle. So we have these bands here, and numerically it appears like you have a connecting orbit that goes all the way from the bottom of the layer to the end of it, but it takes extremely long time. It takes 10 to the 10 iterates. And can you prove that there's no, which means if such thing exists, it means that there's no circle here inside the layer that divides the layer to 2. Okay, and we don't know. So the conjecture is that there's no such circle, but we don't say
that you don't have like a separating orbit in the band. The conjecture is that you don't have a separating
right. That you don't have a Km. So above this band, there are these Km tori that divide the cylinder. You cannot cross them. And numerically, it appears like you don't have it. So here, when you look at 10 to the 5 iterates, you could imagine that this blue line is a dividing circle. It's not. Discover that it's not. You discover that after 10 to the 10 iterates, it actually spreads all along. So whether such things exist or not, we don't know. But that's the conjecture. These are open questions. Okay, but now I want to shift gear into something that may be even more entertaining for you, which is to look at these quasi-integrable Hamiltonian impact systems. So as you remember, we take these sums of what did I do? Okay. Yeah, I take sum of two 1-degree freedom Hamiltonian system, but now instead of putting a wall, I put a 90-degree corner. So, what I want to convince you is what I get is a quasi-integrable Hamiltonian impact system, similar to the quasi-integrable systems that people see in rational polygons, which are either polygons with, so these are, when you look at the billiard, where all the corners are rational multiples of pi, right? And people have worked on these things and showed that you get really interesting dynamics. And now I want to show you that we can get exactly these, or kind of the same kind of things in Hamiltonian impact systems. So the idea is, as before, let us take a sum of two 1 degree of freedom systems and take a surface which now piecewise preserves the symmetries, but it has corners. Okay, and so you see that when you if you hit this part of the corner, P2 goes to minus P2, so this so the constant of motion is preserved, and when you hit this part, P1 goes to minus P1. So the constants of motion are preserved, meaning that the energy surface is foliated by two-dimensional surfaces. Three-dimensional energy surface is foliated by two-dimensional energy surface, but now it's non-smooth, so we don't have the Arnold-Liouville theorem. We don't know that these surfaces must be Turaev, and in fact, I will show you it's genus 2. Okay, so let's see how this goes. Let us indeed just take this system with two oscillators and a corner which is on this side of the, so this will be the minima of the potential, and this is the corner. And in blue, I draw what is called the Hill region. This is all the allowed region of motion for a given energy. And here I plot this energy momentum bifurcation diagram, as I showed before, in which a energy surface corresponds to a given energy. And the energy, and in blue are the level sets which are hitting the corner. So first of all, so now let us look at an energy surface with an energy which is above the energy, the potential value at the corner. So it crosses the blue line, and let us first understand these gray regions. What the gray regions are regions in which the particles do not hit the corner. So it is exactly like in a smooth system, they are going to correspond to tori. Okay, so genus 1 surfaces. We have the blue one, which is vertical. We have the red one, which is horizontal. It has the maximal energy in E and in the horizontal direction. And this one has the minimal energy in E. And when we look at projection of level sets, say that are up here, okay, as long as the vertical energy is not big, it will project to these rectangles. Okay, the rectangles correspond to some harmonic motion like that, right? It's a rectangle because Q1 is less than the maximum of V1 and at this energy level, and similarly for Q2. And so these ones are the ones that are not hitting the corner, and they have a genus 1. Now let's look at the ones at the rectangles that do include the corner. And the claim is that the motion for such level sets is conjugated to directed motion on a cross-shaped surface. It's genus 2. Basically, how do we see it? Basically, we take the smooth system. The smooth system is just a sum of 1 degree of freedom system. We can look at the action angle coordinates in each of these degrees of freedom. Okay, so you get an I and theta for each one of them. Since the level surface is preserved, the I's remain constant. And the reflection, so what does it mean to hit the wall, say, from the right side? It means that you jump from minus P to plus P, which if you start with your angle coordinates 0 on sigma 1, it just means that you go from minus theta to plus theta. And the minus theta is minus theta wall that depends on your action. So for each action, we have a different value of θ1 wall. And saying that you jump from here to here is just saying that you jump from minus θ1 wall to plus θ1 wall. And if you hit the upper part, it means that you jump from minus θ2 wall to plus θ2 wall. So you jump from this part to this part.
So θ1 is decreasing with I1?
Which one? θ1 wall?
Yeah.
θ1 wall is, well, this depends on, so if it's a linear, if it's a harmonic oscillator, then you can, then it will be, let's see, so then it will get close to, so close to the tangency, it gets to pi, right? And as you go away, so when you increase I1, it actually decreases.
Yeah.
Decreases, exactly. But this is for the harmonic oscillator. Yeah. For non-harmonic oscillators, it can be more, I mean, just near the boundary, it's always true. And away from the boundary, it's more subtle. In fact, we'll get, in this case, I think you can show that, so in some cases, you can show it is monotone. And then you are in good, and then you can prove some more things, which we'll get to in a minute. Okay, so what I just showed you is that for these intermediate E1 values, level sets are genus 2 surfaces. And the motion is conjugated to a directional motion on a flat cross, okay? And the dimension of the cross are changing from level set to level set. And the dimension of the cross is changing with the I, and the direction, depending on whether it is a harmonic oscillator or not, is changing. Right? So if it's a harmonic oscillator, it remains constant, and if it's a non-harmonic, it will change with the level set as well. And so now we actually showed that for each level set, we are conjugated to these polygonal billiards, and there is a huge literature on these things, and it is related to many things that I don't understand. But one nicer, I think, understanding of what is so different about those polygonal billiards from the motion, say, on the torus, is that you can have coexistence of periodic motion and, say, orbits which are dense on part of the polygon, okay, for the same level set, for the same direction. So with tori, we all understand that either you are periodic or you are dense. Mm-hmm. And that's called the Witch dichotomy. And for polygonal billiards, it's not true. And so on the other hand, you can prove in some cases that for almost all directions, the motion is ergodic. So the dynamical properties of these billiards is much more delicate than what we are used to in the integrable case or in the hyperbolic case. And now we show that these things that exist on these Hamiltonian impact systems. But now, so when you have a billiard which is polygonal, then you have a fixed shape and you change the direction. Right? Or here we have these energy surfaces in which each level set has typically different metric data. This is just saying this θ1 wall and θ2 wall are changing, and we have coexisting level sets that have different topology. We have the genus 1 level sets and the genus 2 level sets all combined on one energy surface. And so I think this is a very interesting thing, objects to study. There are ergodic properties, perturbation theory, and quantization. There are three directions which we are just starting to get into. Let me talk about perturbation theory. Perturbation theory means that if we say add smooth coupling to the potentials, then we don't have the foliation by the level sets anymore, but the topology of the energy surface must remain. So we are going to create in this way very interesting surfaces, and we need to understand how the motion around them exists. So I will, in the remaining couple of minutes, I will just say the few results we have already in these directions. One result with Christopher Fraczek was to show that in fact we don't have to just look at one corner. We can have many corners. We can look at this star-shaped Russian right-angle polygon, and for all such things, it is possible to prove that for almost all level sets on a given energy surface, you have uniform ergodicity. You can find the genus. So in this way, by including more and more corners, you can have genus 2, 3, 4, whatever you like. And also we have these results showing that when you take resonant harmonic oscillators, you can get, for almost all level sets, coexistence of periodic ribbons and ergodic ribbons, which you can say. So that's what we did for the ergodicity. Another direction is to try and understand what happens under perturbation. So you remember that when we looked at the torus with one wall, we looked at the return map, and for the return map we got this twist map plus a perturbation. Now, if we look at the return map to this same sigma 1, what are we going to get? It's a return map to directional flow on a genus 2 surface. So it's going to be an interval exchange transformation. But now we don't get only one of them, we get a whole family of them. So in fact, we get this, what is the interval exchange transformation? Interval exchange transformation is when you take, here I have interval exchange transformation on the circle. So in general, interval exchange transformation is you take an interval, you divide it to some interval of different lengths, and then you write some permutation. You say that this goes to, say, B, C, A, E, D. Okay, so you are not changing the length of the interval, but you are exchanging these things, and these transformations have been studied again in the ergodic theory, and also they are the natural things that arises when you look at this polygonal billiard and look at return maps to sections in these polygonal billiards, and they have a very delicate non-trivial dependence on the lengths of each of these intervals and on the permutation. And this is in general an interval exchange transformation, and then on the circle, you do the same thing, but you are, in some sense, you think about A, so this could not be on the circle. Yeah, because, okay, if I want it to be on the circle, I should do something like that, EA. They have to stay together, the two parts. And that's what we have here. We have since theta is periodic, the return map is going to be on the circle. So we have this interval exchange transformation where the lengths of these intervals correspond to basically JR are all the initial conditions that jump from the right part of the step, and the K is the number of impacts you have on the top one. So you can have either K or K plus 1 for each level set, and that's the kind of mapping you get. And now when we look at it as a function of I of the level sets, we get families of interval exchange transformation, which is something that, as far as I know, was not looked at, which is a generalization of the standard map. And we can ask what kind of dynamics you have there. And I will just show the pictures. And I should finish, right? And very nice pictures. We don't know how to analyze these things. But, and we have some quantization, which I will probably skip and just tell you that what I try to show today is that we have these very interesting problems coming from looking at Hamiltonian impact systems, which are natural models for classical and quantum Hamiltonian systems with sharp interfaces. And we found two analyzable limits, the near integrable one and the near quasi-integrable one. And there's still a lot of things to do here. Okay, thank you.
I have a basic question in time. There was something called ribbons. Ribbons? Maybe ribbons in one of the, I think it was in the question. Okay, questions or in the result, in some results. It wasn't
A little bit earlier.
earlier,
Yeah, ribbons, okay. Maybe in the, when talking about this.
yeah, ergodic
Here.
ribbons, maybe? Maybe the next one, you just skipped it, I think.
This one, here?
Yeah, this one, periodic ribbons, I mean, ergodic ribbons.
Yeah.
What are these?
Okay, so this is this, okay, so if you have, say, this is, if you have a figure, a billiard, a L-shaped billiard, okay, which is the same by reflection as a cross-shaped surface. Yeah, it's the same. You reflect it, you get a cross-shaped, so it's the same thing. But I think it's nice to demonstrate this with this geometry, with the billiard. So in this billiard, right, you have, for example, a period 4 orbit like this, right? You have a family of it. These are sometimes called periodic orbit ribbons, right? So if you have this periodic orbit, you actually have a whole family of such period 4 periodic orbit. These are the ribbons. And if it was just a rectangle, it will be the whole rectangle, right? But here, once you have this saddle ribbon, saddle period 4, which bounds this ribbon, and then beyond it, you see, with exactly the same direction, you now go into the Macmillan called it the attic. Right? You think of a room with an attic. Okay? So you stay, so the periodic ribbon stays in the room, but then this one discovered that there is an attic. And now you can ask, am I going to connect back or not, right? And this is going to depend very sensitively on the dimension of this attic, right? If it will be somehow in a good rational relation, maybe you will close up and maybe you will not. And if you will not, you will create this dense orbit, which is what I showed in this picture, right? This is the same picture. Yeah, it's a beautiful concept that these people have.
Called a chimney.
He calls it chimney?
He calls it Macmillan chimney.
Chimney, and why? So maybe in another. Right, chimney. Right. Okay. So but I think in another lecture of him, he called it something attic. So okay. So, chimney, depending if you put it up or down.
That's exactly.
It's around Christmas when Santa Claus comes.
With the dense orbit.
I have another question. So in the picture of the triangle, like in the face space, with when you have like the other triangle for the this one, yeah.
Mm-hmm.
So what happens is that you have like tori and then genus 2 surfaces and then tori.
Mm-hmm.
In the examples that you mentioned of like arbitrarily large torus, genus, sorry, arbitrarily large genus. Is it like, what is
it still seems that I was also thinking about it. Do they have to close with tori? And I think they do. I think in all the examples, but we did not. Okay, I should say it this way, that we are still working on trying to understand other topologies. But in this family of billiards of Hamiltonian impact systems, in which you have an oscillator inside this table, okay, and the restriction of the table is that on each quadrant you have like a step-like behavior. This is needed for proving all these ergodic properties. And then, the boundaries here always correspond to either a motion in which you don't hit anything, and then of course you have Turaev, or that you are hitting, say only if you are going, if your energy is large enough, then you go vertically, and then you're going to hit only the two vertical parts, so it will also be a torus. It will be a cut torus, but it will be a torus, non-smooth torus, in the sense that you will have the impact, but it will be a torus. So it seems like the way to see what kind of how many, in this case, to understand how many, what is the genus of the surface appears to be a very simple way. You basically you have your polygon. Have your polygon. This is the center, and you plot the square, which is the projection of the energy level to the configuration space. This is configuration space, and when you plot it, you get a rectangle, and the number of convex angles you have, it gives you essentially the genus. Genus plus this number. And you see that at the boundary of at the boundary, the lower boundary and the upper boundary of any hill region, you will have the horizontal and vertical line, which give you the periodic circles, and around them you will have these thin motion which corresponds to a torus. So you see, these guys never have any convex. So, but this is for this type of. For example, we did not. This if you have a barrier like that. Also, actually, we're now working on such things to understand that. Then it's not as simple as this in terms of the genus, and maybe here. I don't know yet if this has to be true, but for these ones, it's for sure true. That the limiting surfaces are always tori.
So for this example, you have tori and genus 4 surfaces.
Where?
In this example, you can have for this energy level set that you drew.
No, I will have many more, because I drew 2 examples. This is like this.
Anything.
It is it is this plot for. So this is, for example, taking a billiard table in which you have 4 different L shapes which are glued together. Okay, in this way. By the way, okay, and then what you see is that you have these many different triangles which tell you which have to do with the different level sets of these corners. And the gray one means you don't hit anybody. This purple one, I think, means that you hit maybe this level, this corner. Etc.
So in this foliation of the energy surface by these tori, genus higher something surfaces, is the genus jump is always by 1, or can you have like affiliation starting at, you start from the bottom, you have Taurus.
Yeah.
And then can you move up and then suddenly end up at like a genus 5 surface without?
I think
going
this goes back to this comment that for these ones, whenever you include another corner, you increase your genus by 1. So if you are a symmetric case, you can immediately you can do it all together. But
So
if you are in a non-symmetric, for generically you will not, right? On the other hand, if your table also includes say another little region like that in the interior, okay? So your table is this part, right? Then I did not. I know that here each corner will not. Here the corners can I think add more than just 1. So it depends. I have to do. I think we did not conclude this case, but it's we did not complete this whole thing. But I think it's not. I mean, it depends. For example, also this works that we did on the ergodic properties, they work only for these kinds of shapes. For example, if we put the corner in positive, so imagine that your origin, the minimum of the potential, is in here, and the corner is up there, then in fact it does not fall into this category. And I think, and for that, we don't have any results on the ergodic properties of such systems. Such systems have these orbits that have almost tangent behavior, which are excluded here. So it's different. So again, it's something that I don't really know what are the properties there. It's still work to be done.
Thank you again.